Nice. Time, so let's start today's seminar. Uh, the speaker is Anirban from Seoul National University. He will talk about the mesoscopic quantum systems to detect light dark matter. We start when you're ready.
Thank you very much, Suro, and thanks very much for coming and for the invitation. As Suro mentioned, I'm a postdoc in Seoul National University, and I work mostly on broadly astroparticle physics, but mainly in the dark matter and neutrino phenomenology stuff. So today I'm going to tell you about what's recently been happening in the sub-GeV or the light dark matter direct detection experiments, and also maybe about about a couple of topics on which I'm working in the related field. So let's get started. As the usual thing these days, I was playing with ChatGPT, and I asked it. You cannot see the question here, but it's like, what is the future of direct detection experiments for dark matter search? And it actually nicely came up with a few different points. There are actually more. I just cut out the rest of it, but you can see that one of these points is the light dark matter and axion. So, and there it actually describes very nicely what's the significance of doing dedicated search experiments for light dark matter, and also related to that is to use advanced detectors and materials and advanced technologies, more innovative technologies that we need for doing this kind of light dark matter search experiments. So I just thought that this is nice that it already highlights these two very important, crucial points about light dark matter detection that lies in the future of this area. So with that, here is a brief outline of my talk. I'll give a very broad description of different ways for how people are thinking of light dark matter detection experiments. And then I'll tell you about two different projects on basically a proposal of new way to detect dark matter using power deposition and sensing, and then using graphene or bilayer graphene. And finally, I'll touch upon this idea of how can we use the synergy of quantum computation, which has been hot topic lately, and light dark matter experiment techniques. So this is a plot. Probably some of you have already seen. Is like this shows the whole mass range of the dark matter particle, which is possible, and you can see that it extends almost like 90 orders of magnitude from 10 to minus 22 electron volt to 10 to the 67 electron volt. So it's huge. So we need we need a very broad and expansive experimental program to look for dark matter. And of course, we are already doing that but there are some specific parts of the parameters where more of our resources and experimental efforts are more concentrated. And so here you can see some of those points. So this classic WIMP regime between like tens of GeV and TeV is probably the most familiar one. And if you read the dark matter papers from 90s, you would see neutralinos and supersymmetry dark matter all the time. And that was the most favorite parameter space for dark matter to look at this time. And even today, we have several different experiments still going on. And there are also other, there's this QCD axion particles at much lower mass scale. And but of course, in between there are many orders of magnitude that we need to still probe, and we need different types of experiments to do that.
Sure. How can we determine this is kind of simplification? How can we determine the best range between the two values? Just the best range is imposed by theory or experiment?
Right. Yeah, that's a very good question. Actually, that's not a stupid question at all. So the lower bound. So you're basically asking how we are getting this lower and upper bound of dark matter mass, right? Yeah. So the lower bound comes from the something called dwarf galaxy observations. So we have many different dwarf galaxies around our Milky Way, and we know that because we know that the dark matter is non-relativistic, so it has to have a de Broglie wavelength at least of the size of dwarf galaxy. It cannot be smaller than that. And 10 to the minus 22 EV is roughly that scale. So if dark matter is smaller, lighter than that, then the de Broglie wavelength will be smaller. But we observationally see dwarf galaxies, which are cloud structures of dark matter. So that gives you the lower bound. The upper bound comes from the lensing of so so if you have a like 10 to the 67, which is like tens of solar mass, you cannot. These are not elementary particles. These are macroscopic dark matter objects, and you have lensing constraints on them. There are also other constraints from black hole, like accretion constraints. But overall, that's the limit that they give on the higher mass end of dark matter. Yeah.
Yeah, but still any strong evidence that we can assume the dark matter is must be relative to.
Sure. Yes, there is, and so I guess the one thing that comes to my mind is the structure formation, the history of structure formation. So earlier, even until the 80s and 90s, people did believe that dark matter could be hot or cold, and they did simulations of structure formation, and the structure formation history, the hierarchy of structure formation, like when do smaller structure form and when do larger structures form. So this hierarchy that depends on the hotness of dark matter. And then they did simulations. They had that theoretical predictions. Then we did the observations, and when we matched the simulations with the observations, we saw that the dark matter has to be cold. It cannot be hot.
So kind of strong evidence.
It is a very strong. Yeah. Nowadays you cannot find anyone talking about hot dark matter anymore. Yeah, we know that dark matter has to be cold. It is non-relativistic. Okay, so I told you about this classic WIMP regime. So there are many different direct detection experiments that are going on. You probably know the names of these: Xenon, LZ, Panda X in China, and then Cosine in Korea. And there are actually many more. So all of these experiments, they're looking for dark matter in the mass range of few tens of GeV to TeV or tens of TeV, and the way they look for dark matter is they have a detector with some noble liquids. In this case, xenon. They have two phases: the liquid xenon and the gaseous phase at the top. So the idea is that dark matter would come and hit a nucleus in the detector, and it will the nucleus will recoil, and it will ionize some the surrounding particles, and you will see the signature of that. So these type of experiments have been going for more than a decade, actually more than a couple of decades now. And this is the current scenario of this in this parameter space. So this is a dark matter mass, and this is a dark matter nucleon cross section. So the most stringent constraint that we have today is from the Lux Zeppelin, the LZ bound that they released last year, and and we are still waiting for a future data release from all of these experiments. And at some point, they don't show it here, but at some point, these bounds will hit the neutrino floor at the bottom of this parameter space, and it's going to be more challenging after that. But that's like the heavier part of the parameter space. But then there is the sub-GeV or sub-MEV part of the parameter space, which requires our attention. Why? Because there are many dark matter models with which you can populate this part of the parameter space. So I'm showing here two plots on the left. Yeah, so these are basically, again, the same dark matter mass and dark matter, in this case, dark matter electron scattering cross section. The left one is for heavy mediator. And by mediator, I mean the particle that mediates the interaction between dark matter and the visible sector. And the right one is with the light mediator. So here you can see, and both of these plots are taken from this paper, and you can see that there are many plethora of models which predict dark matter electron cross section in this part of the parameter space, and this gray area is the region which is currently excluded by experiments. And if you compare this cross section with the previous one, you can see that it's like they're going up to below 10 to the minus 47, and it's only here minus 37, 38. So it's like we still have a lot of parameter space to cover here. And interestingly, that most of these models are sitting just below the current exclusion bound. So we can expect to see some of these models getting ruled out in near future. Similarly, in the light mediator case, there is this famous bound. There's this famous band of freezing models, and it's an alternative way to produce the current relic density of dark matter, alternative to the freezer, which is a more popular one. Here too, you can see that it's sitting below the currently excluded constraints, and some of these are stellar cooling constraints, which are to some extent questionable. But these are like laboratory experiments. So we can see these experiments going down by a few orders of magnitude within 5 or 10 years, maybe not 5 or 10 years.
So in this case, the effective interaction between dark matter and electron is dark matter electron in the effective language. Is that correct?
Is right in the effective language, that's the case. That would be more appropriate in the heavy mediator case when you can integrate out the mediator. But for the light mediator, it would be it could be like a dark matter. So there could be a common mediator that talks both with the dark sector and the visible sector. So you can write down a dark matter, then the mediator, and then electron. This kind of diagram.
Okay.
And the mediator mass would be very light. Effectively, you can say massless.
I see.
And also, just to mention, the interaction type also could be very different. It all depends on the model which you use to describe the interaction, vector, scalar, or dipole type interaction.
So where is the neutrino flow?
Yeah, that's a good question. Yeah, that's there in the next plot. So just to quickly answer your questions, this is again this is not the dark matter electron, but this is the dark matter nucleon cross section. Of course, for the neutrino floor, you have to have the dark matter nuclear cross section, not dark matter electron cross section.
I think there's also
From electron interaction, not sure. There might be, but I'm more familiar with the dark matter. I'm sorry, the neutrino nuclear scattering. mostly from the coherent 7s scattering. So in the dark matter nuclear parameter space, this is the neutrino flow. So yeah, so those were the model space, and here what is the future? What the future looks like in the dark matter scattering, dark matter electron scattering, dark matter electron and dark matter nucleon scattering space. So these plots are taken from the last year's SNOMAS process, and they have basically labeled different types of experiments, experimental proposals or ideas in near term and far term. I think in the near term, they club together all the experiments which could be done within 5 or 10 years, and far term is even beyond that. And this orange band is a key milestone. So these are the parameter space that's more important theoretically, and we like to rule them out. So yeah, so it's going to be very interesting how this process goes on in the near future. Now, technically, for the sub-GeV dark matter direct detection experiments, the issue is the difference from the WIMP-like dark matter is that the recoil energy is very small. So this plot that I stole from a talk from Felix Wagner, this shows the recoil spectrum of nucleus as a function of the recoil energy, and for different dark matter masses. So you can see that so this is the heavier dark matter and this is the lighter dark matter, and currently the lowest threshold that has been achieved in all of the direct detection experiments is roughly about 10 electron volt, which is in the super CDMS experiment, also I think the CREST experiment, and of course there are many proposals of experiments even with even lower threshold, and but this is a current state of the art. So we have to look for sub-GeV dark matter. So you can see that this corresponds to roughly 0.2, maybe a bit above 0.2, so roughly 1 GeV. So to go below 1 GeV, we need to go to even lower energy, and the recoil energy or the dark particle energy that's transferred by dark matter to your detector that scales with the dark matter mass, because dark matter is non-relativistic. So that's a goal. So of course, for sub-GeV dark matter, you cannot use nuclear recoil, because nuclear recoil that requires you to have that requires dark matter to impart a certain, at least a few keV of energy to the detector, to the nucleus, to actually recoil the whole nucleus. But for sub-GeV mass in the MEV range, it's not possible. So here this plot shows the different types of processes, relevant processes in the different energy regimes. So this is the dark matter mass, and this is the recoil energy. And this dashed line is the mean energy of dark matter in the Milky Way halo. So you can see that from the heavier end, we have these liquid nobles, the noble gas or the xenon, LZ, all these experiments. But below there, it's you have to use ionizations in the semiconductors, like basically the an excitation of electron from the valence band to the conduction band. And even below that, we have the phonons in the detector material. I'll talk more about phonons, what exactly they are. But that's something that we have been using. And then even below that, there are even smaller energy scale materials where, for example, semiconductors, superfluid heliums, and single phonon detectors. Some have already been used as in dark matter experiments, but there are many more ideas. So you can see that as the dark matter mass goes down, we have to use different detection techniques, and I'll talk a bit more about a couple of these. But on the other hand, there is an advantage of actually going to lower dark matter mass because again, because it's non-relativistic, the number density of dark matter goes up with its smaller mass. So actually, for lighter mass dark matter, you don't need a big detector like xenon to have a relatively good constraint. You can actually have a very small tabletop type experiments and get nice constraint in the dark matter parameter space. So that's one good thing. So one idea that has been used for many years now is the charge detectors, or the CCDs. You're probably familiar with the term CCD, which is basically everywhere in your cameras or mobiles and stuff. So the idea is basically, as I said, that you have some semiconductor in your detector, and this all material has this electrons. They sit in the valence band, and then there is a gap of the order of maybe a few eV between the valence band and the conduction band. And if you give enough energy to the electrons, they can excite to the conduction band, and you can detect that. You can apply electric field, and the excited electron can drift, and you can detect that current. So that's the idea of CCD, and they have been used in few dark matter experiments called Sensei and DAMIC. The newer version is called DAMIC M, and there is a future experiment proposed called Osculator. And these type of experiments have the strongest constraint in this sub-GeV parameter space, like between MEV and GeV parameter space right now. So these blue lines are from the latest one from Sensei. So this is again, of course, you can imagine this is between dark matter electron scattering. So this is again heavy mediator, light mediator, and this is dark matter absorption. So instead of scattering, you can also absorb dark matter in your material, and that could also give an charge excitation signal. So Sensei has this strongest bound today. And there are, of course, they're going to improve their detectors, and these are the projections that they are going to have in future.
Sorry, could you go back to slide? So in this case, the energy in the dark matter mass you can detect depends on the mass gap. Is that correct?
Right. So it doesn't depend. All right. Yeah, you could say depend on the mass gap. So what the mass gap does is it gives you the lower threshold or the lower limit on the dark or on the energy that you can detect. So yeah, your device cannot detect any energy excitation below that gap. So that's the threshold that's the threshold here in all these experiments.
Okay. So
and in the towards the higher mass. I'm sorry.
Okay, so let me check my understanding. So when the dark matter mass is around 1 MeV, the required energy is around 1 eV or something like that.
Yeah.
So and typically that corresponds to the mass energy gap.
Right. Okay. Yes. So that sets the threshold in your experiment. So the gap is basically setting the threshold. It's not for CCD. It is for any experiment. If you have a gap, that's your threshold. And towards the higher mass, that depends on how well you can reconstruct. So, for example, if the dark matter mass is, or the energy that dark matter is imparting is much larger than the gap, then it would excite many electrons. But then you have to reconstruct all this electron energy that then you have to say that, yes, this is an event, this is a scattering event. And that capability decides how far you can go.
And I have one more question. So how much this kind of experiment depends on the structure of band of semiconductors?
I'm sorry, structure of what?
Structure of bands of conductors. Band structure of metal. Yeah.
Do you mean like, what do you mean by structure? It's like exact topology of the bands?
Yeah, topology of the bands or anything.
Um,
The general band structures of metals or semiconductors.
it's very hard to build a detector with a normal metal, because in a metal, so what's happening in a semiconductor is the Fermi energy is right at the top of the valence band. So there is no electron in the ground state. There is no electron above this. But for metal, the Fermi energy would be somewhere here, in the middle of the band. In that case, even you can just give an infinitesimal amount of energy, and that would excite some electrons. So that's not a very good detector. You need a threshold in your detector. That's why semiconductor is good. But about like the exact structure of the band, I'm not very sure. Probably you need a very well-defined. If the bands are like, so in practical, it's not very smooth like this. But it's actually, if you look at the dispersion relation of the bands, electrons, it's actually much more complicated. But
So maybe once the electron is produced, it's like a free electron because we are considering semiconductors.
Yeah.
And we can detect. That's all.
Yeah, right. So of course you need a good amount of band gap, like a few eV. That's a typical number for semiconductors. But other than that, I'm not sure how exactly it depends. I mean, of course, the exact band structure will depend on will determine your experimental sensitivity, but that's a qualitative thing. Sorry, that's a quantitative thing. I'm not sure how. If you need a particular type of bands or anything, at least I'm not sure.
Thanks.
Your work is solved by using semiconductor.
I have not come to my work yet, but
Yeah, then your work is related to graphene.
yeah.
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 Then,
Yeah, graphene it has a very different type of band structure, if you're familiar, but
that is you have not used any semiconductor.
no, but graphene, the way I'm going to use graphene, that's still called a semiconductor-like state, because there is a gap between the valence band and conduction band. So yeah,
And in the case of graphene, you know the band structure.
Yeah, that you can calculate very precisely.
The band structure of graphene is quite simple.
Yes, I would say so. Yeah.
That is also the reason why you are considering graphene.
There are other reasons also. I'll tell you a bit more when I come to it. Yeah.
All these experiments, does it always have to be, there should be a band energy gap, or it can be some other techniques also? If you have a lattice or something, like fully occupied lattice, and let's suppose by heating some quickly, by the dark matter interaction, you change the structure of lattice. Is it possible, or does it always have to be some band gap and you are moving one electron or two valence band to the other?
Right. Yeah, that's a very good question. That was also I was kind of alluding to earlier. So the gap is kind of important in dark matter experiments, is because if you have for example, take this case, for let's say this silicon has a band gap, let's say 1 eV. Then you can cool down your system below 1 eV. So I mean the temperature below 1 eV, so that there is no thermal excitation in your system. and all the electronic noises also go down. So in that case, you are basically removing all the background. So you only detect those events which are above this band gap. So that helps you given like a barrier from the noise in the environment. So that's why any gap is important.
That will set a one limit on this.
Yeah.
Below that limit, below that threshold.
Yeah.
You cannot.
Oh, yeah.
Anything with this.
Right. Yeah. So yeah, that's it. That's what I said earlier. That yeah. So in all dark matter constraints, you would see that these bounds go up very sharply at some lower mass. So this shooting up here is because of that threshold.
But removing background is very attractive. Yeah, just you said, the reason why we introduced the semiconductor is to remove the background arising from thermal fluctuation.
Right. Yeah. We are using semiconductors just to probe this part of the dark matter mass, but having a threshold in your experiment is important to remove the backgrounds.
And if we getting lower the temperature more and more, then we can use the semiconductor with the smaller band gap energy. If we lower the temperature of experiments.
I'm not sure if I got your question right, but because I mean, this band gap is a property of the material. You cannot decrease the band gap, but by just decreasing the temperature.
I mean, if we control the temperature of experiments,
Yeah,
then we can make the temperature lower and lower. Then we can choose another semiconductor with the small band gap.
Oh yeah, right.
Yeah. Because at that time there is no temperature fluctuation.
Right.
Yeah. I
Yeah.
understand.
Right. Yeah. So there are actually more ideas of using even lower threshold material. So semiconductor does not have much more lower threshold than typically of a few fraction of EV, but there are other materials. Okay, so let me go ahead. Okay, so that was the charge detector. So even below, I said that there are phonon excitations that could be used for dark matter detection. And if you have forgotten everything about phonons from your high school, just give a brief introduction. Phonons are basically the oscillations or acoustic oscillations in your lattice. So this is just a very schematic figure of a 2D lattice, and phonons are basically the oscillations on this. So if you can, when the momentum transfer by dark matter scattering is of the order of inverse of the lattice spacing, which happens to be in most of the materials happens to be of the order of keV, then the phonon excitations becomes important, because dark matter does not have enough energy to recoil a single nucleus, but it has enough energy to create an oscillation in the lattice. And these are basically phonons, and there are detectors. There are sensing devices with which you can detect actually phonons. So, and in this energy range, so below typically 100 millielectron volt, this lattice vibrations becomes a major or the more dominant energy transfer or energy deposition mode. And now of course, to calculate the scattering rate for any sensitivity of any experiment, you need to calculate how many phonons you can excite from a dark matter scattering.
So how do you describe the interaction between the matter and phonons?
Right. So that's what I'm going to tell you in maybe in the next slide. So for any lattice, you can actually break up the whole lattice. Lattice is basically a periodic structure, so you can actually define an unit of your lattice, which you can use to build up the whole crystal. So, and here, this is just an example of such an unit which has 2 atoms. So in general, it can have n atoms, and there would be 3n number of acoustic modes. Sorry, there would be 3n number of phonon vibration modes in the lattice. And they have 2 types. One is the acoustic mode, and one is the optical mode. Generally, you can say that in the acoustic mode, all the atoms in this unit cell, they move in the same direction. So it's like they are oscillating in unison. And for the optical mode, you can say that they are oscillating, the different atoms in the unit, they are oscillating in different directions with different velocities at the same time. So they kind of somehow cancel their momentum, but they still have some energy. So, and because we are in 3D, so every crystal has 3 acoustic modes, at least 3 acoustic modes, and the rest of it, 3n minus 3, would be all of them would be optical modes. So these are 2 examples of phonon dispersion curves. So this is the phonon energy, and this is the momentum, basically the omega function of k relations. So, and aluminum, aluminum has only 1 atom in the unit cell, so it does not have any optical mode. It only has 3 acoustic modes. So, and you can see here these 3 acoustic modes, these 3 lines. And this is an example for silicon. It has 2 atoms in the unit cell, so it has, of course, 3 acoustic modes and also additional 3 optical modes. So the difference, the qualitative difference between acoustic and optical modes is in their behavior in the low momentum case. So this is the momentum. So in the low momentum case, all the acoustic modes, their energy go to 0. And these are basically normal sound waves that we are familiar with. But the optical mode, they have some non-zero energy. So you can see this from the vibration type for this optical mode. So they are vibrating in the opposite direction. So their momentum perfectly cancel. So they have 0 momentum, but still they have some energy. So that's why they have a finite energy at 0 momentum, and this creates a gap in their dispersion relation. And if you have any questions from this, you can ask me. So with all that, that's just a brief detour about the phonon theory of phonons. But let me now go to how you actually calculate the dark matter or the phonon excitation rate from dark matter scattering. And so here is the general formula. Here is the general formula of so gamma is the scattering rate, and of course there are many quantity factors here, but there are some simple ones. Sigma is the scattering cross section. F chi is the dark matter velocity distribution. We know this roughly Maxwell-Boltzmann in the Milky Way halo, so we have to integrate over that distribution. And so this S is the most important quantity here. This is called the dynamic structure factor. It's a material dependent. It's a detector. It's basically the response of the detector to an energy and momentum transfer of omega and q. So it encodes all the information that's there for the detector. And it's different whether it's a CCD or phonon device or nuclear recoil or whatever. And F mediator Q is a dark matter form factor, which I was telling earlier. There are 2 types of cases, light mediator and heavy mediator. So depending on that, it can take different forms. And then you integrate over all momentum, and you get the total. I think there should be an integral over energy also, and then you get the total rate. And this is a spectrum as a function of energy. It's basically the same thing, just except this delta function. Right. So this is the.
I couldn't understand. So maybe the same question. How do you describe the interaction between lattice system and dark matter?
Right. Yeah.
Maybe we can write some Hamiltonian or Lagrangian of lattice which has interaction to dark matter.
Right. So what you need is basically, yeah, maybe I should have added one more slide explaining that. What you need is basically any interaction between between the nucleus of the material and dark matter, and that gives you the channel, the interaction channel between the dark matter and the lattice. And when you then you can actually calculate this structure factor, this S functions, assuming that phonons are the only degrees of freedom in your system. And so okay, so this is this dynamic structure function is the detector response of the system for a given energy deposition omega and a momentum deposition q. So then the next thing is what Kiyoharu is also asking, that how do you calculate this S function? So this S function depends on your energy range and momentum range. But if you are in the phonon regime, you can actually calculate the dynamic structure function starting from the first principle, like the calculating the basically write down the phonon excitation in the momentum mode. Then you can calculate the 2-point functions, and then you take the Fourier transform from the real space and time to momentum space and energy, and that's how you can calculate this dynamic structure functions.
What is LA and LO?
Right. So then, so there are then once you realize that your dark matter is exciting phonons in your lattice, there are different channels. So as I said, depending on the lattice, there are different phonon modes. Right? There are 3 acoustic modes, and there are also optical modes. And so by LA, so A means acoustic and L means longitudinal. So I think I forgot to mention one thing. So here in this picture, so one of these would be longitudinal and the other 2 would be transverse. So longitudinal means basically they are oscillating in this direction, and transverse is the other 2 directions. Similarly for the optical modes. So there would be different structure factors, whether the phonons are acoustic or optical, whether they are longitudinal or transverse. So these are the final expressions of the structure factor for different types of excitations.
BJ is a brilliant.
Right. So so again, you can divide your whole computation regime in the momentum space into 2 parts. In one, when the momentum is smaller than the Brouwer zone momentum, and one is higher than Brouwer zone. And they have different behavior also. So in this case, it's more coherent. So it's like many crystals are oscillating in coherence, but in this case, they are incoherent. They are oscillating differently. So you can all do all this. It's a pretty messy calculations and a very long one, but actually not done by me. This was from this paper, and you can actually come up with pretty good approximations, analytic approximations for these structure factors.
Where does it come, the knowledge from the neutron scattering?
I'm sorry.
Where does this knowledge from neutron scattering come in? You have already.
Oh, okay. Okay. So that I have not told. Oh, yeah. That I have not told you before. Told you yet. Okay. Why did I write that? Oh, I wrote that because okay. So, so if you go to this paper, they do all these analytic calculations, but the calculation actually follows the already existing theory in the neutron scattering, because in the area of neutron scattering, they also basically doing the same thing. They are scattering neutrons with different types of materials. Their aim is different. They want to learn about the different materials, their crystal structure and stuff. But they use this exact same theory. So we can also do that. We can also now use that for dark matter experiments. So that's why I said that it's we are using the knowledge from neutron scattering, which is very well known, and people have been using that theory for many years now.
Sorry, I have a stupid question. Why we should consider only neutron scattering? There is a proton.
Right. No, so they use neutron because they want to avoid the Coulomb interaction. So for example, the one aim is they want to know what is the crystal structure of the material, and that you can do by doing this. I'm not sure if you're familiar with Bragg scattering and stuff. They basically shoot neutron on the material, and they look at the spectra of the scattered neutrons, and you can figure out if you do the Fourier transform of the scattered spectrum, you can figure out what is the crystal structure.
Heating material is neutron.
Yeah.
Yeah.
Right.
Just
Because it's neutral. Because it's neutral.
Yeah. Because in order to investigate the structure, you
Right.
need to avoid the Coulomb interaction.
Right. Yeah. Exactly. Exactly. Yeah. So if you could use proton, but then that adds an additional interaction in your theory, and it's complicated. Yeah, so the point is that these are some of the ideas that are already existing in different areas. So we are just using this in our dark matter community now.
So you show only longitudinal mode here. Transverse mode is not important.
So that's a good question. So it turns out that transverse mode is not very easy to excite in this energy range. It's mostly would be the longitudinal mode which would be excited. It depends on the exact structure, the oscillation pattern of the different modes. So it just happens that longitudinal mode is easier to excite.
Is there a strong reason to understand why transverse mode is not evolutionary?
I mean, as far as I know, it just comes out of the mathematics, but I'm not sure if there is any nice physical argument for that. But typically, I mean, not typically, I mean, it's always the case. The lowest lying band would be the longitudinal one, and the higher band would be the transverse band. And because oh no, okay, it's saying it wrong. Oh no. Yeah, that cannot be the reason.
Both longitudinal and transverse mode should pass zero. I mean, both longitudinal and transverse acoustic modes are basically Goldstone bosons.
Yeah, right.
But they can have a different slope in principle.
Yeah.
So different sound speed, right?
Yeah, right. So
what you are saying is probably transverse mode has a larger sound speed. Is it?
So I think I misspoke. I think longitudinal mode has higher sound speed. Higher sound speed.
Longitudinal mode.
Yeah, I think so. Because you are basically pushing two atoms in the same direction, so that requires more energy. So I think it's easier to distort a crystal in the transverse direction than in the longitudinal direction. So I think.
But this is optical versus acoustic.
No. What I mean is that so let's say you have just two atoms in your unit cell. So in the longitudinal mode, they are oscillating in this direction, right? And in the transverse mode, they are going like this.
Yeah.
So what I'm saying is that if you imagine this as a spring problem, it requires more energy to excite an oscillation like this than this mode. So that's why I said that the sound speed for transverse mode is less than the longitudinal mode.
But the omega is C times K, right?
Yeah, right. So, but you can choose the same K. Same K, but yeah.
That means the transverse mode has a smaller energy, right?
That's my guess. I'm not sure, but that's just my intuition right now. I mean, yeah, there could be even more complexities in this. So it's a crystal, right? It's not isotropic. Not all reactions have the same sound speed. It also depends on the direction of the momentum. And yeah, there are many more details. So yeah, right. So this is a brief summary how you can actually calculate analytically the phonon excitation rate in a material like aluminum or silicon. And here is an example of the structure factor in the previous slide. Again, for this one is for aluminum and this one is for silicon. This right line here, this is a longitudinal acoustic mode. Same here, but silicon has also this optical mode. So there's this additional branch here. And this vertical line in the middle is the pure zone. And above these, there are multiple phonon excitations possible. So that gives this broad, this bright line. And yeah, so that's basically just the result of these analytic calculations. Now I'll finally come to the work that I did with Noah and Rebecca. Here is the archive number. So the idea is to use so far I've said that all these experiments are trying to detect dark matter, individual recoil of dark matter in the detector. What we are suggesting is that now we have so sensitive devices which can detect very small amount of power deposition. You can actually look for dark matter deposited power instead of doing this integral of scattering rate over energy, which gives you the total scattering rate. You can use the power deposited, so it's just multiplied by energy, and then you integrate, you get the total power. So this is a simple schematic picture. Instead of this looking for this individual recoil, you are looking for multiple scattering, and that gives you an power signal in your system. Apart from halo dark matter, this idea could also be important for another population of dark matter, which is called captured dark matter. The idea is that if you have relatively strong scattering between dark sector and visible sector, then you can capture a good amount of dark matter around the Earth, not only Earth, or also around the sun or any star or any astrophysical objects. So what that does is it creates a shell of dark matter around this object, and but they have the very low energy. So basically they are getting captured and they are thermalizing with the local temperature, which is very small, so 300 Kelvin something. And
this document is solar light.
It's through scattering.
Self-interaction?
Not you can have self-interaction, but you don't need. You can just have interaction.
The scattering with the electron or is large enough to.
Yeah, electron or nucleus or anything. So you can have the dark matter. Once they get captured, they can scatter many more times, and eventually they will thermalize with the local temperature. And of course, that's why they have very much lower energy compared to halo dark matter. So for the same mass, you can see that they have of the order of 10 milli-electron volt energy, and that translates to a velocity of 1 kilometer per second. So it's very small. And but the upside is that the number density of this dark matter will be very high, because they are getting accumulated for a long time. And according to some calculations, this number could be 13, 14, or 15 orders of magnitude more than the halo dark matter number density. It's like huge number. So that gives you also an advantage in this power sensing experiments that I'm going to tell you about. So we proposed 3 different types of experiments. Actually, we took the data from 3 different experiments. So number 1 is a quantum device based on aluminum superconductor. So this is the schematic of the experiment. So this is the superconductor, which is junctioned with a normal metal. In a superconductor, what happens is that in the ground state, all the electrons, they form Cooper pairs, and this and that's the ground state. The BC is ground state, and to break a Cooper pair, you need to give it some amount of energy. That's a gap energy. And that creates this. If you look at the energy diagram of the system, you will find this gap, which is for aluminum that happens to be 0.34 millielectron volt. So this is actually not a dark matter experiment at all. They were trying to make a device which can stay free of any stray quasi-particles. I think their goal was to make a device which can stay free of quasi-particles as long as possible. And what they saw in their data is that there is an equilibrium density of quasi-particles or these excited electrons from these Cooper pairs. And we took that number, and because we know the energy that requires to break one Cooper pair, you can translate that density to power deposition. So this is the number that we found is roughly a few times 10 to the minus 25 watt per micrometer cube. So this is the power density, so power per volume. And you should also note that this is one of the smallest power that ever been detected in any experiments or anywhere. So that's one experiment. So here is another one. This is again a superconductor based, but this was a different experiment, and they are trying to develop a single photon detector, which are important for example, some telescopes like JWST to detect very faint, far away objects. So in this case, they also have some superconducting aluminum, and they are shining photons on this piece of superconductor, and they are trying to see if they dial down the intensity of this photon source, how many photons they can actually detect. So this is an important graph here. So this is the expected number of photons, and this is actually the observed number of photons. So these 3 data sets are for 3 different intensity levels, and you can see that for the lower end, even though they should not see any photons, they are actually seeing some amount of activity, some amount of photon counts in their system. So that can also be translated to a power deposition, and that gives us this number of roughly 10 to the minus 20 watt per micrometer cube. The third one is actually a dark matter experiment. This is called Super CDMS. So here they have a silicon or germanium, a silicon detector, a substrate, and that is covered with superconducting aluminum. And that again, in turn, connected with tungsten transition edge sensors, which are basically very sensitive sensors to detect small amount of energy. So the way they are doing this experiment is that they think that dark matter will come in, and that will excite many phonons in the silicon substrate. These phonons will travel into the aluminum, will break some Cooper pairs, and some of these broken Cooper pairs or quasi-particles will then travel into these transition edge sensors, which will get detected in the device. But of course, in our case, we are looking at this experiment in a different way. So even before starting to do the experiment, they have to calibrate their device. So they have to say this. So this is the 0 level. This is the this is the like zero energy or zero power that their device is measuring, and that we can use that number as the background, or I'm sorry, not background, as a minimum that they can detect. And we found that a number like 3 times 10 to the minus 21 watt per micrometer cube again. So these are the 3 numbers that we use in our work, and here is the result. So this is in the mass range of like mostly below GeV, and this is again the dark matter nucleus scattering cross section. The orange line here is a quasi-particle from the number that the constant from the first experiment that I told you. This magenta one is from the super CDMS, and actually what happens for the second experiment, that is not very sensitive enough, so it's like sitting up here beyond this plot range. So you can see that so, and the gray regions are the already existing constraints. So you can see that it getting very competitive, and these are very new experiments, and we are still improving. I mean, they're set to improve, and in future we might see some new parameter space that could be excluded by these experiments. These two are for halo dark matter, and this is for the thermalized or the captured dark matter that I told you. This area is actually not limited by the sensitivity of the experiment. This is actually limited by the evaporation limit of captured dark matter. So there's another thing that we have to take into account here for dark matter capturing, is that if dark matter is very, very light, then they can, after getting captured, they can even get kicked out by the thermal velocity of the Earth, and that puts a lower limit on the dark matter mass that you can capture efficiently in any object. And for Earth, it happens to be here. So yeah, it's just unfortunate that we are limited by that evaporation limit. So yeah, so this is the main result of our work, and we'll see if any future experiment that can do even better than this. And I was also looking at in different types of materials. So there are superconductors from different elements possible, and these are just some preliminary results that from tungsten silicide or lanthanum telluride. They can give an even much better constraint than those ones. So we are still working on this. Because I'm running out of time, and just quickly go to the second one. Is still the work in progress. I'm working with some graphene experts in my department in Seoul National University. So probably all of you know what graphene is. Graphene is basically a layer of carbon atoms arranged in a hexagonal shape. And of course, a single layer of graphene is semi-metal. So if you look at the dispersion relation of electrons in the graphene, it's like so the energy momentum relation looks like this, and this is the Dirac point, and they meet. So the valence band and the conduction band, they meet at a point. It's called a feature of semi-metals. But if you have 2 layers of graphene on top of each other, something like this, then the dispersion relation can change. It has a different structure, and even on top of that, you can gate this bilayer of graphene. So it can actually apply a potential across the layer, and that opens up a gap between the valence band and the conduction band. So it's actually a tunable band gap system. So we are trying to use this kind of system so that we can have an experiment with tunable threshold.
Yeah. What's the second line dispersion relation? The oval at the triangle.
Oh, this one?
Yeah, this one and other.
Yeah. So those are actually more bands. I mean, it's not that the electrons will have only just one valence band and one conduction band. There are actually multiple bands if you go into higher and lower in the energy range.
There are two valence bands and few conduction.
You could say that, yeah. Right. So there is another concept of twisted bilayer graphene, which has been very popular in the last few years. After it's been described that they can also show superconductivity, and so here is an experiment from this paper where they develop a single photon detector using twisted bilayer graphene. So what I mean by twisted bilayer graphene is just a bilayer graphene, but then the layers are twisted by a very small angle. And there are these things called magic angles, certain few angles at which this bilayer graphene will show superconductivity. So if you more details, you can go into this paper and check out the details. But the only thing is that it becomes just like the superconducting aluminum that I showed earlier, and you can again use that small energy gap in the system as a threshold in the device. So yeah, we are trying to use that, and for the when dark matter interacts with electron, there is a very nice way to calculate what is the scattering rate, and that's using the linear response function or the dielectric function of the system. So this was identified in this paper a couple of years back, and so the idea is very simple. So the dielectric function is basically so this is a function that condensed matter people they calculate every time, or they measure experimentally every time whenever they are trying to look at a new material, or they're trying to look at the structure of the material. So this is one of the first functions they try to calculate, and it basically encodes the information of when you shoot a beam of photon in the material, how much energy it loses, and we can use that same quantity for dark matter scattering also if you have a dark photon like model, when there is a kinetic mixing between photons and dark photons. So that's the idea, and once you have the dielectric function, you can convert that to this dynamic structure function that I described earlier. It's just proportional to the imaginary part of the negative inverse of the dielectric function. It's also called energy loss function. It basically says how much energy the photon loses inside the material. And it's a very nice one that in this paper that was identified. We can use this function because it's very readily available for many different materials. But the problem is that the energy and momentum range. So the condensed matter people, they are not always interested in the same energy and momentum as the dark matter community. So you might have to go back and do the experiment in a different momentum or energy range, or you have to compute it theoretically. So right now we're still doing those calculations, but I can maybe so this is a scattering rate, but I can maybe show some preliminary results. So this is the dark matter mass and the dark matter electron scattering cross section. So this is the same freezing band that I showed in one of the earlier plots, and so this TL line here is the limit that we can get from twisted bilayer graphene with a mass of 10 milligram and running an experiment for 1 year, which is like, and if this result holds up, then it's very interesting that actually it can go below the freezing line. And this line here is just from bilayer graphene, and which is also rules out a certain portion of the parameter space. And the plot on the right-hand side is for dark matter absorption. And for comparison, I also showed the lines from the superconducting aluminum for the proposal. This is not an actual constraint, but this is also a proposal. So yeah, these are like we are still working on this and trying to calculate the structure factor in a more refined way, and probably we'll have this paper out maybe in a couple of months, hopefully. So finally, I can tell you just one thing about the synergy between quantum computation and low mass dark matter detection. So I guess there are right now multiple companies that have developed quantum computers. So Google is one of them. So on the left, you can see the Sycamore chip that they have developed. I think it has like, yeah, it has 54 qubits. Qubits are basically the units of quantum computation. So the more qubit you have on a single chip, the larger the computing power of your computer. And so that's the goal. You just trying to put in as many qubits as possible and do some complicated calculations. But the prerequisite for that is that you have to have a coherence, the quantum coherence across all these qubits for a certain amount of time to perform a particular calculation. And that's limited by the environmental noise. So for example, in this paper, they were looking at the Sycamore qubit chip and trying to identify what are these what are these environmental noises. And so one of them is, of course, the cosmic rays. So they come in, they scatter inside the substrate, they emit phonons. These phonons will go into the qubit layers and they destroy the coherence in the whole chip. And that happens all the time. So that's one of the limiting factors. So their goal is to isolate the whole qubit chip from these environmental noises. So now we can see that there is a very similarity between this diagram and the Super CDMS device that I showed earlier. It has the same type of substrate, silicon, and they are on top of that, there are some superconducting layers, and they are also trying to see these experimental perturbations or energy transfer. And but of course, we are trying to detect dark matter, and they are trying to develop a quantum computer. But of course, there is this technical similarity between these two types of programs that we can actually exploit, and maybe with some cross collaboration or cross talking between communities, we can perhaps achieve our goals much more easier than doing it separately. So there are some programs that have already started on this. So there is this Nexus collaboration at Fermilab. So they are trying to do some experiments in some underground lab at Fermilab on this. And if you are more interested in this direction, you can check out this nice colloquium on YouTube, where they talk about this.
Who is the speaker?
That's a good question. I don't remember the name, but yeah, here's a URL if you want. So yeah, this is just a couple of slides that I wanted to highlight, that there's this nice synergy between these two communities that I think we need more collaboration between. So that brings me to the conclusion of my talk. I'll just say that this dark matter parameter space is very fast, and there are many orders of magnitude that we have to look at. So we need different types of experimental techniques, new ideas. And in this talk, I told you about two of these ideas that I'm personally working on, but we need more new ideas and also new technologies to actually put more constraints in the dark matter parameter space, and also collaborative strategies strategy between quantum computation community and the actual community would be very helpful here. So with that, I'll stop, and if you have any questions, I'll have to take.
Thank you for the nice talk. Any question?
Would you please go back to page 33?
Sorry, page of.
33.
Okay.
This, I think the constraints are given by calculation.
Yeah.
Yeah, just so you write down pretty line. Yeah, then
Right.
my question is, in order to obtain the real constraints, then we need to establish several experiments about this. Right? Yeah, then the corresponding experiments about the corresponding experiments, how do you think when it is constructed fully?
Sorry, the experiment is what free?
Just in order to draw the constraint.
What is the
constraints,
how I can calculate this?
No. I mean, in order to obtain the real constraint, then
Okay.
we need to establish any experiments, or we need to construct indeed the experiments. We need to make a machine, several things. Yeah. So my question is, when the corresponding experiments can be established in.
Oh, okay. So you're basically asking how feasible this kind of this experiment is with graphene.
Yeah. No. When is it established?
Is there a real experiment which is looking for this kind of thing? That's what
Okay, so if that's also no, at this point there is no experiment, dark matter experiment that's are looking for this kind of signals. So yeah, so this would be our proposal. So yeah, of course there will be many technical challenges to do this. For example, graphene. The one problem with graphene is that it's a very light material, like right. So if you look at the surface density, mass density of graphene is like 10⁻⁸ gram per centimeter cube. Centimeter square. So it's very hard to get a good amount of graphene and put it in a single detector and do some measurement. So maybe you have to make multiple arrays of graphene and then somehow multiplex all these components. So yeah, there could be many technical challenges, but of course something that we have to look at.
I was wondering, when can we check the constraints from the real experiments?
Oh, okay. That depends, like how. But for that, you have to do an actual experiment. So, yeah, that brings in much more sociological questions. Like you have to convince a group, you have to get funding and stuff. Of course, I mean these would be very small scale experiment, tabletop type experiments. Doesn't require much room or much money, but still, it's a you need. I mean, of course, I cannot do this experiment tomorrow. I need collaborations, experimental collaborations. But of course, it's the same for any other dark matter experiment. Yeah.
Another question? Okay, none less than. Okay. 네네. 녹화만 끄고요.
Let me just check the page 4. Of course, small.